hit. Okay, welcome back to Organic Chemistry 2341. We're going to go ahead and continue with chapter 1 and also continue, move on to chapter 2 today. Don't forget to take the quiz from 11 a.m. to 11 p.m. today. If you can't get in, go ahead and email me. I know a couple tricks. Usually it's quitting the browser and reopening the browser. And only having Canvas, that usually works. If not, sometimes it's login issue. You have to be logged in with your net ID. Anyway, those usually cover most of the things. I'm not seeing chapter 2 notes on Canvas. Let's double check that. I thought I unloaded it under student version. It shouldn't be under, yeah, it's under student version of Solomon's chapter 2. Oh, it's not released yet. That's why. All right, I am releasing it right now. It should be published. Oops. Publish. There we go. Update. Update. There you go. That refresh your Canvas page and it should show up. Is there supposed to be an access code for the quiz? No. There is not supposed to be an access code for the quiz. You need to quit your browser and restart your browser. Proctorio should handle that completely behind the scenes so that you can't even see. In fact, I can't even see what the code is because it's protected. So, but that should help it. Okay, I'm going to go ahead and share my slides. And I gotta do that and this. And that and this. All right, so this is the slide we ended on last time. I'm going to go ahead and move my gallery view over here just so I can watch all the angry nodding when we go through things. No, okay, so I can just see everybody here. I have the chat open, so go ahead and ask questions or unmute to go in the chat and we will continue. Okay. So the idea here is we learned to draw we learned to draw Lewis dot structures last time. And the Lewis dot structures basically told us where the valence electrons were. Those are the ones that bond, and how those valence electrons are arranged around different molecules such that they could try to fill our octet. And so if we look at our structure we see here, we have an octet around that oxygen, an octet around that oxygen, an octet around that oxygen. And if we get all that out of the way, we have an octet around our carbon. Okay, each of those atoms has 8 electrons around it. So that means that these are happy, or they follow the rules of Lewis dot structures. So now, let's say, the right side of the class drew this one, the left side of the class drew that one, and the center of the class drew that one. Who's right? Well, everybody, because all 3 are correct Lewis dot structures. There's no reason why it has to be these 2 oxygens that have charge, or these 2 oxygens that have charge, or these 2 oxygens that have charge. Does oxygen always need 4 groups around it? Okay. Now, oxygen likes to bond twice and have 2 lone pairs, okay, because it has 6 valence electrons, so it has 2 lone pairs and it tries to bond twice for a total of 8 electrons. Remember, each of those lines is 2 electrons, okay? So the question was, does oxygen always need to have 4 groups around it? When we write it with the electrons, yes, it'll always have a total of 8 electrons, usually 2 lone pairs and 2 bonds. Occasionally, as we saw when we calculated formal charge, we can actually have 3 bonds and 1 lone pair, but it will have a positive charge. So in those cases, we're going to have a total of 4 sets of electrons, 4 pairs of electrons, either bonding or not bonding. Does that answer your question?
Yes, thank you.
Great. Okay, so in the case of this, we found that we could draw 3 different resonance structures, and they're all valid resonance structures. And so that means that in resonance theory, in our heads, we have to think, well, it's not really number one, it's not really number two, and it's not really number three. It's some kind of blend of these. So if I have number one, how am I going to switch number one to number two without breaking any rules of Lewis dot structure? Well, the idea here is that we can move electrons and we can break that second bond. That second bond is known as a pi bond. We're going to learn a little bit more about that today. The first bond is what we call a sigma bond. So there's one bond, the first bond is the sigma bond. The second bond is the pi bond. We can move lone pairs and pi bonds around and even charges around by moving electrons to create the other Lewis dot structures. So in this case here, we want to convert from Lewis dot structure 1 to Lewis dot structure 2. Okay, so to do that, what we have to do is we have to take this double bond and turn it into a single bond, and turn this single bond into a double bond to make it look like 2. So all we're going to do is move electrons. We do not break any of the bonds between the different atoms, except for double bonds. Double bonds are 2 electrons, and we're going to move those electrons. So let's look at what we do there. So remember, when we move 1 electron, our arrow has a single barb on it. When we move 2 electrons, we have 2 barbs on it. So in this case here, we're going to move 2 electrons from this lone pair in to form that second bond, that double bond. When we do that, these 2 electrons come up here to give us our charge. Okay, so now let's look at that. So now it looks exactly like this number 2 structure. Okay, we didn't move any atoms. We didn't break any primary bonds, those first bonds between all the different atoms. We didn't add or remove electrons. Okay, we didn't add or remove electrons, but we did move where they were. Okay, so in this case here, we took those 2 electrons, moved them up here to create a second bond, a double bond. And we took this double bond and had those 2 electrons move up here to form our charge. Now we can do that again to form our third structure. In this case here, we're going to move these lone pair in here to create the double bond. And then we're going to move these lone pairs up here to create the charge. So that's going to be 2 electrons from that pi going up to become a lone pair and a negative charge. And now we've seen that our C double bond O structure moves from the top to the left to the right. Okay. And all we did was move electrons. All right. So that's the key thing we're going to do when we do resonance structures. But we have some important differences here. Resonance is not equilibrium. Equilibrium is when you had an acid and a base and they didn't completely react to form water and what the salt was. They only formed partially, and that means they went back and forth between the acid and the base and the neutralized species. Okay, that's an equilibrium where you have the different materials. In resonance, this is just a theoretical vision of the electrons moving around. Okay, so it is not in equilibrium. It's because it can be in either one of those structures, but it can be either of those structures or either of any of the structures if there's more than one. So we indicate equilibrium by having 2 arrows, one going one way and going the other way, saying the reaction can go to the left or to the right, depending on where it is. In fact, it's somewhere in between the left and the right, and that's at equilibrium. In the case of resonance, it's saying that that's a double-ended arrow. Either one of those Lewis dot structures is correct. And the reality is it's probably somewhere in between in what we call a resonance hybrid. So equilibrium is the 2 different arrows with single barbs. Resonance is the double-ended arrow. Okay. So we actually have some rules about this. The first rule is that, well, these resonance structures are kind of just to help us understand that these electrons are moving around. Okay, so they don't really exist in any one single form. It doesn't really exist 100% here or 100% here. It exists somewhere in between the two. But by drawing both of the resonance structures in this case and having that resonance structure arrow between them, it's saying that either one of those would be the reactive species in our reaction. Okay, so because any single one might be inadequate. So for example, let's say we had this thing and it reacted with something where the positive charge was. And if we call this, if we call this carbon, carbon 1, and this carbon, carbon 3, and we looked at the products and we saw that how many things reacted with carbon 1 and how many things reacted with carbon 3. If this was the only resonance structure, 100% of the reaction would take place at carbon number 1. Okay. In contrast, if this were the only resonance structure, right here, 1 and 3, 100% of the reaction would take place at carbon number 3. But because neither one of those resonance structures accurately portrays what is happening here, that's why we have that little double-ended arrow here. It means that in our reaction, we're going to get products on carbon 3 and products on carbon 1. Okay, so what does that mean? Now, if they're equal in energy, being that they are equal amounts at any one time in the solution, going from one to the other, then we're going to have equal numbers of reactions at 3 and equal number of reactions at 1. So this actual experiment is how we figured out that there was resonance. Okay, because we saw that not only do things happen at carbon number 1, but an equal number of things happened at carbon number 3. That means that these two equivalent Lewis dot structures are somewhere, the reality is that's flipping back and forth between the two because it was explained by the reactivity. All right, questions on that? After moving electrons and pi bonds, do we know where the charge will go? Yes. By counting the number of electrons or calculating a formal charge, you get where the charge is. Now, there are 4 rules, and this is one of them actually, is that the overall charge of a resonance structure, this is rule number 4, does not change. Means if you have 2 negative charges on one of your resonance structures, you will have 2 negative charges on your other resonance structure, and you will have 2 negative charges on your last resonance structure. It's also true that if you started with a negative charge, a 0 charge, an uncharged species, you have to have an uncharged species in your resonance structures. Okay, and I'm going to show you something that demonstrates that. The first rule is the position of the atoms in the molecular ion do not change between any of the resonance forms. We do not move atoms. Okay, their position and their connection between all the other atoms is the same. Excuse me, is the same. Only electrons participate and move. Okay, sigma bonds, that first bond that we make in between all the atoms, does not break ever. Okay, that same connection between sigma bonds and atoms does not change. However, we can move. Thank you. Somebody blessed me in the chat there. We can move pi bonds, that second bond, but we never break those first bonds. Okay, so our 4 rules are: the positions of the atoms in the molecule do not change. Only electrons move. Sigma bonds, the first bond between all the atoms does not change. The second bond can. And the overall charge of the resonance structure should not change. Okay, so let's demonstrate these rules on a couple different ways. Okay, the first and foremost is we have to have a proper Lewis dot structure. So we can say, oh, well, we have two charges, it balances out to 0. So maybe this is a good Lewis dot structure, okay? Well, let's double check it to make sure, because we want to make sure that we have 2 electrons around hydrogen, 8 electrons around oxygen, and 8 electrons around carbon. So if we look at this, we have hydrogen, which has those 2 electrons. Remember that bond is 2 electrons and it gets to count both. So that's good. 2 electrons, 2 electrons, and 2 electrons. So the hydrogens are fine, okay? So let's go ahead and look at that oxygen here. Okay, now oxygen has a charge on it, but that's okay. We can say that because we have 3 bonds to oxygen. We have 3 bonds to oxygen, and if we calculate the formal charge, it gives us a +1. But let's count the number of electrons we have. So this bond has 2 electrons in it, this bond has 2 electrons in it, this bond has 2 electrons in it. That's 6. Plus the lone pair is 2 more, which is 8. Oxygen has 8 electrons around it. It has a full octet. All right, hydrogens are fine, oxygen's fine. What about the carbon? Okay, so the first thing we notice when we look at this carbon is we have 1, 2, 3, 4, 5 bonds. Okay, that means there are 10 electrons around carbon. Can we have 10 electrons around carbon? No, we cannot have 5 bonds to carbon. Therefore, this is not a correct Lewis dot structure. Therefore, we cannot take this and use it to make other resonance structures, because this Lewis dot structure is not right. So let's look at, yes.
Does hypervalent mean excessive valence electrons? Is that what they mean by hypervalent carbon? Is that like a real concept?
Yeah, hyper meaning more than valent meaning more than it can have. It has a higher valence than it can have. It has a total of 10 electrons. That's 2 more electrons than it's allowed. It's only allowed 8, therefore it's hypervalent. Okay, so what we're saying is that it has too many electrons in its valence shell.
It would have like a charge of -2, right?
In that case, it'd have a charge of -1, because let's see, 1, 2, 3, 4, 5. If we did our formal charge, it'd have a charge of -1, because we'd have 4 valence electrons minus 1/2 the shared electrons, which is 10. So 4 minus 5 is -1, and then there are no lone pairs.
Oh, yeah, you're right.
Formal charge would be -1. Okay, good. Hey, we even got to do formal charge. Oh, by the way, I'm going to put forth, we already found the error that there are too many electrons in that nitrate ion. And so I will be adding a thing to the website about how to correct that. So, all right, I'm sorry, the YouTube site on how to correct that. Okay, so we have to have a Lewis dot structure that's valid first, and we can only move electrons. So let's look at this right here. We have around here, we have 8 electrons around this one, 8 electrons around this one, 6 electrons around this one, but it has a positive charge, okay? That means that it started with 4 electrons, it shared 3 of them, and then gave 1 away to give us a total of our formal charges +1. That's a valid structure because our total molecule has a fixed charge, okay? Now, when we look at our neighboring resonance structure, we see, number 1, it has the same number of valence electrons total. It has the same charge. So they both have a +1 charge. They both have valid resonance structures. Okay, so how do we convert from one to the other? Well, again, only electrons move. So electrons can move from lone pairs or pi bonds, okay? So all of these bonds right here, I'm going to draw in red. These are all sigma bonds. These are all the first bonds that are connecting the atoms together. We call those sigma bonds. And I will talk a little bit about their nature in a little bit, but I wanted to demonstrate that there. And then this last bond here, this pi bond, is 2 electrons. and we can move it. So we can move these 2 electrons to here. And when we do that, the pi bond now is over here, but carbon is now missing those 2 electrons and ends up with a positive charge. So this is 2 valid resonance structures. We're not moving any atoms. We're not breaking any of the sigma bonds. We're only moving the electrons from the pi bond to a new pi bond. And we have the same charge total on both structures. Do you see how we're following all 4 rules? Okay. Now, is it just positive charges that can do that? No, we can do that with negative charges too. In this case, we'll actually see a full lone pair on carbon move around. So this is the one we saw, and we saw that the charge was the same and the electrons were the same, etc. Now let's change the number of electrons. Let's add a couple of electrons comparatively. And so now we have a lone pair on this carbon. So it has a total of 8 electrons around it, okay? But because it's not bonded one more time, it's only bonded 3 times, it has a negative charge, okay? So if we did that formal charge of the, it has 4 electrons, 1/2 of the shared electrons, which is 3, and minus the 2 electrons in the lone pair gives us a -1 for formal charge. Now here it's easier to see that these electrons are going to kick in to give us our double bond, and then these electrons are going to kick out to give us our lone pair. So the electrons are kicking in and kicking out and going back and forth. Okay, do we see how that is a valid resonance structure, even though the charge has changed? Is it okay to have less than 8 electrons? Yes, if there is charge. You're allowed to have less than 8 electrons if there's charge. But you want to have, even if you have a negative charge, if you have you want to have 8 electrons, and it can have charge or be neutral, but less than 8 electrons, you typically have to have charge. All right, so now we have to think of, okay, in the ones we showed you before, there was really no difference between either one. It just moved the charge from carbon 1 to carbon 3. That's all it did, was move back and forth. However, you can draw valid Lewis dot structures that have a difference in their charge. Now, what that means is if one is uncharged and one is has charge somewhere in the structure, then that means the one that is neutral is going to be more stable. Now, I said one of our rules is you cannot change the charge in your Lewis dot structures. Okay, so let's look at this one. Let's look at this one right here. So if we look at this one, we have 0 charge on this Lewis dot structure, right? Okay, let's look at the other one. We have a negative charge and a positive charge. Well, those cancel out to give us a 0 net charge on the molecule. We did not break rule number 4. However, there are 2 charges here. Let's look at those charges and see if those are valid. Right here, in this case here, we have 6 electrons around carbon, but it has a positive charge. And in this case here, we have 8 electrons around oxygen, but it has a negative charge. So that means that both of these are satisfied as far as trying to fill their octet, but having a positive charge on carbon when it doesn't have that. So this is a valid Lewis dot structure. But one has charge, even though they cancel out, one doesn't. The one that's completely neutral is always more stable, and therefore it's going to be the major contributor. Can every atom, not just carbon, have less than 8 electrons if it has a positive charge? For most of the things we're going to do carbon, nitrogen, oxygen. We'll want to see 8 electrons around them in neutral compounds. If they have less than 8 electrons, they might have a positive charge. Things for like boron, which break the octet rule, don't have to have 8 electrons. Does that answer your question, Holly? Yes. All right. So
that is a resonance structure. They are resonance structures. It's just The left one would be like, I'm just throwing a random number out there. If you were to like do a chemical reaction with it, the left one would be like 90% higher or something in amount. I'm just throwing a random number out there.
Yeah, right. It would be significant. It would be significantly more stable. But remember, these two structures don't exist. They only exist on paper. Okay, so we don't see this.
Okay.
It's not like there's an equilibrium here. All right, we do have things that'll go back and forth between the charge species. We'll talk about those later. But this is just saying, oh, we can move these electrons around. Okay, so this is going to be our more stable version, but the fact that this could be drawn means we might see that affecting how it reacts. Okay, so just keep that image of this in your head, and we'll talk about this in a couple more slides.
I have a quick question.
Yes.
So is it better to always draw the more stable Lewis structure first to then be able to create the less stable one to kind of see like where to go?
Yes, it's always easier to draw the most stable one, the one with the most connections that follows all the octet rules. It's usually easier to draw that one first. See how if you drew this one first, all you'd have to do is kick these electrons up here, giving you the positive charge here and the negative charge over here. So the more substituted, the more neutral Lewis dot structure is usually the more stable and the easiest one to draw. Okay.
Thank you.
Okay. So again, these don't exist. They're just showing us that we can draw them. Okay. And because they do exist on our head, we might see that they could be contributing to reactivity in the future. But I just want to show you that they are contributing resonance structures. They don't actually exist, but one is definitely more stable than the other. Okay, so how do we get from one to the other? I showed you that we push electrons around using these curved arrows. And these curved arrows are very important for the fact that if the curved arrow has a single barb, we're moving one electron. If the arrow has two barbs, we're moving two electrons. So that's important. And we also want to always look for direction of electron flow in our reaction mechanism. So what we're always going to do is we're going to say, where are the electrons starting from? And we're going to go from there to where they're going to be connected to, or where they're attacking, or where they're reacting. Okay, so we're always going from the electrons to the thing that doesn't have the electrons. That way we know which way things go. We never show movement of atoms. We only want to show where the electrons are going. This is where we're going to get used to seeing how the mechanisms work and how those things work in our resonance structures. So for example, let's say we have this right here. We have a positive charge here, and we do not have electrons to move over here. It has a positive charge. That means this is not correct. We always start with the electrons and move to where they're going to be. Okay, so in the case of this nitrogen here, we have this lone pair of electrons. It's going to go ahead and attack the carbon because those electrons are the ones that are moving. Now, this is kind of weird. I have this carbon written very funny. I have this delta negative up here and this delta positive down here. Remember this resonance structure here? We said that this one was more stable, but this one is valid. So that means that it's more like this. I'm not going to draw an arrow to it. It's just more like this. So that means it doesn't have a full negative charge or a full positive charge. It has a partial delta negative charge on the oxygen and delta partially positive charge on the carbon because of this resonance structure. Okay, so that being said, we now know where the electrons are going to flow when we see a carbon double bonded to an oxygen. And we call that the carbonyl group. We know that we're going to have those electrons are going to flow to the part that's partially positive. Okay. Now, in the case here, we don't have any lone pairs of electrons to play with, so they're not going to come and attack this electron here. So that's not right. Now, do you only move one pair of electrons? No. In mechanisms, we sometimes move multiple pairs of electrons. And in this case here, we have the electrons from the OH are going to come over here and create a new bond with this hydrogen. That's going to end up creating water over here, okay? But we already had a bond between the hydrogen and the oxygen on the other compound. So we have to take those two electrons and put them on the oxygen, giving us a negative charge. Okay, so in the first two cases, we're only moving one pair of electrons to either make a bond or to make an attack. In the third example, we've moved two sets of electrons to affect the reaction. All right, do we understand how to use curved arrows to show where the electrons are flowing?
Yeah.
Why wouldn't the molecule stay in its most stable state? Well, it does spend most of its time there, but the fact that it has that resonant structure possible means that it will have some portion of that resonance form is going to show up in its reactivity. So like the question before, if it's 90% one way and 10% the other way, that little 10% is going to influence how it reacts. Okay. So it's the major contributor is the more stable, but that minor contributor will control how it reacts. All right. So I have a question here. Isn't the bond breaking in the third example between O and H? Okay, so there is a bond breaking between O and H, and there's a bond making between O and H. In this case here, I'm going to change colors to red. We're going to take these electrons here and reach out and grab that hydrogen. And when we do that, those electrons are going to create a new bond between the hydrogen and the OH oxygen. Okay. At the same time, we're going to go ahead and change. These electrons here have to go somewhere. This bond now has to break. So those electrons from that bond go and stay on the oxygen as the negative charge. So does that answer the question? Is the bond breaking in the third example between O and H? Yes, we're breaking one bond between O and H, but we're making a new bond between a different O and the same H.
So it's like okay to kind of break it as long as you negate what you did basically and keep everything connected to something.
Yeah, so if you notice, we only moved electrons, the net charge of the two molecules exactly stays the same. Okay, all right. Okay, so the third example here shows that you can move more than electrons at one time. And remember, in the resonance structure with the carboxyl with the carbonate, we actually moved lone pair electrons, and then we also moved double bond electrons. We can move those at the same time. So two sets of electrons moved in each of those examples. Okay, so can we extend that? Yes, we can actually have a resonance structure where we have double bond, single bond, double bond, single bond, and a ring. And guess what? All three of those can exchange to give us our new resonance structure. In fact, this happens so much, and we'll learn this in the second half of there, that they continue to flip around the ring and around the ring. And so a lot of people draw the resonance hybrid, or the equivalent of all the structures, as a ring in the middle, because the electrons just keep going around and around and around. So this is what we call our hybrid, our resonance hybrid. Okay. And when we have resonance hybrids, we're going to see those in brackets. See how we have brackets around here? So these are the two resonance structures that we can draw. This is the average or equivalent of those, the hybrid structure between the 2, 3, or 4, sometimes even 4 resonance structures we have. Okay, so let's show that again with a different compound. Let's go to this next one, the carboxylate ion. In this case here, we have a lone pair with a charge. We're going to move that in to create a double bond, and we're going to lose this double bond and create the anion here. Okay, so this is a valid dot structure. This is a valid dot structure. Okay, so that means the reality is somewhere in between. The hybrid structure is somewhere in between. So if this one has a double bond and this one has a double bond, neither one has a full double bond in our hybrid structure. We have the partial double bond. See this dotted line here? That's a partial double bond. And instead of having the anion just here on the lower oxygen or the anion here on the upper oxygen, it's actually spread between the two oxygens. So that double bond is spread between those two oxygens and the charge is spread between the two oxygens in the hybrid structure. Okay, so this is the hybrid structure. BRID, hybrid structure. Okay, so again, we're starting with a molecule that's negative, we're ending with a molecule that's negative in our hybrid, in our resonance structures, but the hybrid is somewhere in between. That double bond is spread between those three atoms, and that charge is spread between those three atoms. Okay, let's do one last example with ozone. Ozone turns out to have a positive charge and a negative charge on it all the time. But if we look at the resonance structure here, we can move the electrons in from this one and out from this one to move the electrons from one side to the other, one side to the other. Okay, now this positive charge and this negative charge cancel each other out. So that means ozone is neutral, but it has two charges. This negative charge and this positive charge cancel each other out. So again, the molecule is neutral. So, but when we look at the hybrid structure here, the charges have gone away. The charges have been canceled out. So all we have is a partial double bond between these two oxygens and a partial double bond between those two oxygens. Okay, questions about that? See how we're following the rules of Lewis dot structures, and we're following the rules of resonance to create that hybrid, that blending of those different possible Lewis dot structures. Okay, does the negative represent two electrons? Not always. The negative just means we have more electrons on that atom than we have protons. So negative is literally our formal charge that we calculate. And so it's the comparison between the valence electrons we have and the number of protons that are in there. Okay, so negative charge does not always represent two electrons.
So when we see like negative and positive and they cancel out, we're just assuming that they have the same value.
In this case here, the formal charge on oxygen is negative. The formal charge on the other oxygen is positive. The molecule itself is neutral. But when we calculate the formal charges, we're going to see this has one more electron than this one. That's why it has actually it has two more electrons than this one, because this one has only 5 electrons when it's supposed to have 6. This has 7 electrons when it's only supposed to have 6. So one's negative and one's positive. Okay. All right. So if we have a possibility of more than one of these resonance structures, we want to think of what would make it more likely to be one versus the other. Okay. Now the real rule is that the more bonds and the fewer charges, then the more stable the resonance structure is. The more bonds or fewer charges, the more stable the resonance structure is. So if we compare this one right here, it has 4 covalent bonds, 4 of these bonds between these 4 atoms. Okay. In this case, we have 3 covalent bonds and 2 charges. So this has 3 covalent bonds. So that makes this one more stable, more likely to contribute to the resonance hybrid. Okay, so if we were to draw a resonance hybrid here, we would start with the most stable structure and HH, and then our carbon is going to be there in the middle. And we don't say we have a partial charge or a partial bond between the oxygen and the carbon, because it is the most stable form. But we do say in our resonance hybrid, this has a partially positive charge and this has a partially negative charge. So our resonance hybrid would look like this structure here. The bonds, more stable, is the major contributor. This is the minor contributor, and it contributes the partial charge. Does that make sense? Okay. All right. So we have Lewis dot structures that we use from our valence electrons. If we can write more, we have resonance, but we can see which of the resonance contributors contribute more to the hybrid. The one with more bonds, the one with the more stability contributes more to the hybrid. Okay, so the other thing that can help us determine this, if we haven't seen that, is the structure where the more of the atoms have a complete valence shell. Okay, so the structure where more of the atoms have their valence filled, like for oxygen, nitrogen, carbon, it'll be 8 electrons. For hydrogen, it'll be 2 electrons. Okay, and for boron, it'll be total of 6 electrons. So the one that closestly represents the filled electron shell is the one that's going to be more stable. So if we look at that rule here, again, we have 6 electrons around this carbon. So it's going to be less stable than this carbon, which has 8 electrons around it. It'll be less contributing to the resonance hybrid. All right, questions on that? Okay, so we've kind of played with the idea that, you know, we're bonding, we're making this covalent bond between 2 atoms, okay? And we're doing it by sharing electrons. But fundamentally, how do they get close enough together to share these electrons? So if we think about it, the outside of every atom is the electron cloud, right? And the nucleus is in the middle. And if you have a neutral atom, these electrons completely cancel out the positive charges in the nucleus, and the molecule itself is negative. But the outside of the shell is negative. There are electrons there. So what happens when an atom comes close to an atom? They see the electrons first, and they try to repel each other. So at some point, at some distance here between the nuclei, all they see is the negative repulsion from the electrons, and therefore there is no way to get these to go together. However, if you get them close enough such that the electron from one of the atoms is being attracted to the nucleus of the other, and an electron from the other one is being attracted to the nucleus of the other, there's now an attraction because this electron is being attracted to the other atom. This electron is being attracted to the other atom. And when we do this, we start to push against that electron-electron repulsion because we have a positive negative attraction. Excuse me. Okay, so if we start doing that, what we're going to see is that when it gets to a certain point, we're going to have it equilibrate. This electron is attracted to this nucleus equally with this electron being attracted to this nucleus. And we're going to come out, and so the attraction force is equal to the repelling force of all the other electrons, okay? And so what we're going to end up doing is finding a nice even space. So the attraction is pulling them together, the repulsion is pushing them apart a little bit, but there's a bond here now. We're equally sharing these 2 electrons between these 2 nuclei, and it's going to have a fixed distance because of energy, and it's going to be nice and stable. Now, what happens if you try to squeeze them together even more? Well, the electron-electron repulsion, or the positive neutron, the nucleus repulsion will force them apart, so it'll take more energy. So that's why they don't get too close together, and that's why they don't get too far apart, is they found this balance between the attraction between the shared electrons in the nucleus and the electron-electron repulsion, or the nucleus-nucleus repulsion. So what we see here is that all of our bonds, depending on the size and number of electrons shared, are going to be a certain length because of the balance between the repulsion and attraction. Question on that? Okay, so how can we use this to our advantage? Well, we can look at how the atoms bond. Okay, so if we first looked at how we filled our electron shells, we filled up 1, and that's our core electrons, and then we started with 2. In this case, we're looking at carbon, so we have a total of 4 electrons. However, if we were to bond this using these 2 electrons and then these p orbitals here, the bonding structure would look really weird, because remember, this p orbital is on the y-axis, this p orbital is on the x-axis, and this p orbital is on the z-axis. So what it would try to do is try to bond these hydrogens 90 degrees apart, and then these 90 degrees apart, and then this one would have to be shot off somewhere over here at like 110 degrees somewhere over here, because that's the one that's bonded to the s orbital. Okay, now the problem is we don't observe that. Okay, we don't see the hydrogens at 90 degrees apart and the one hydrogen off in the distance. What we see is 4 equal orbitals. When we look at it by X-ray crystallography or any other way, we see that we have 4 equal spaces between all 4 hydrogens, and they're as far apart from each other as they can in 3D space, which is 109.5 degrees. Okay, we call this a tetrahedral structure. Tetra meaning 4, hedral meaning solid, or dimension, solid. And then what we see here is that they're spread out, and so we have 4 sigma bonds between carbon and hydrogen that spread out equally. Okay, now if we looked at this model here, it would not spread those 4 hydrogens out equally. They would be different. They would not be equal. So that means something has to be happening. Okay, so what's happening is that we are, instead of having our, by the way, there's no electron here. If instead of having our electrons be in our s orbital and then our electrons being in our p orbital, what it's going to do is it's going to raise the energy of the s a little bit, lose a little energy in the p a little bit, and blend them together to give us 4 equivalent orbitals. Okay, so we had 1 orbital here in the s, 1, 2, 3 in the p's. So we have a total of 4 orbitals when they blend together. Now, what's the point of blending them together? Well, now, number 1, they're all of equal energy. They're all of equal shape. And if they're all of equal energy and all of equal shape, that means they can spread out as much as they can in 3-dimensional space, which turns out to be 109.5 degrees. Okay, so by doing this, number 1, we get to bond more evenly all the way around. We have less electron-electron repulsion from groups too close to each other, and we get 4 equivalent bonds. Okay, so this is one of our driving forces for hybridization. So what does that look like? Well, when we started out, we had our 2s orbital, which is of course spherical. Okay, it's completely round. Okay, does this affect any other than the bond angle? It's the bond angles the way we see it most, but yes, it also affects the way it bonds. How do you go from 5 electrons in the ground state to 4 electrons in the hybrid state? Like I said, there is no electron in this orbital here. That is a misprint. We have 2 in the s and 2 in the p before we hybridize. Okay. All right. So let's look at that. So we have our s and it's spherical right here. Okay, and so that's okay. Then it can bond anywhere. But then we had the p's, and the p was 1 on the x, 1 on the y, and 1 on the z. Okay, that's what would give us our 90 degrees apart right here. So what we're going to do is we're going to blend a little bit of round with a little bit of dumbbell. Okay, but it's not going to evenly distribute over both sides of the dumbbell. It's going to be on one side of the dumbbell or the other. So in the case here, this side of the dumbbell gets bigger, this side of the dumbbell gets smaller. This is the side that has the S blended into it. Okay. And then this, a little bit of the S is blended into this one, a little bit of the S is blended into that one, a little bit of the S is blended into that one. Okay, so now we have those large ones here, but we have these little tiny lobes on the here, right? So if we look at that, how can we squeeze those together? Well, the bigger lobes right here, the blue lobes, are going to be spread out as far as they can get, which is 109 degrees. But when you look at it really carefully, the little teeny lobes are squeezed in between the big lobes. So that little side of the lobe is actually squeezed in between those on all four of those points where they meet. Okay, so that's how we've taken two different shapes in four different orbitals, turn them into four of the exact same shape, but just pointed in different directions. Now we have four equal orbitals that are the same shape and they're the same energy so that they will bond equally. Okay, do all tetrahedral molecules have hybridized orbitals? Yes. In fact, what we'll see is your oxygen, carbon, and nitrogen, all of our group 2s, are all sp3 hybridized to start with, and then they can change hybridization when they change shape. So all tetrahedral molecules tend to be sp3 hybridized because you have four equal orbitals. Okay, and we're going to see as hybridization changes, shape changes. In fact, that's how you'll be able to tell when something has changed hybridization. The shape changes. All right, so let's continue on. So now, what does that kind of squeeze together and look like? Well, remember that these lobes are just mathematical concepts of where the electrons are going to be about 90% of the time, right? So we can also look at it as, well, okay, we have a little bit of density here and a little bit of density here, and that's on the y-axis, and on the x-axis, and on the z-axis. And our orbital here is going to be spread into each of these to give us the larger lobe and the smaller lobe, all equal in energy, all equal in size, and all equal in spacing. So how does that work with making the molecule? So that's just the hybridization of the carbon. So if we look at that, we had four electrons, four valence electrons, right? It's in group 4A. So we had four valence electrons. We took them out of the S and the P's and blended them all together to make them sp3, so they're all equal. And now that they're all equal, they're tetrahedral. So each of those orbitals has one electron in it to share. So when it comes close to a hydrogen, it also has one electron to share. And we share these two electrons and create a sigma bond. Okay. It's a primary bond between the carbon nucleus and the hydrogen nucleus. Okay. And then let's get to another orbital, do the same thing. We get a sigma bond, that sigma, sigma bond, sigma, and a sigma bond here. So notice, after bonding, this carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And they're evenly spaced. The only way we can evenly space is to have four equivalent orbitals. Therefore, we had to hybridize the S and all three P's. S plus three P's total 4 equal orbitals. All right, questions on that? Okay, so I'm going to skip that one. Sorry. So how do we make carbon-carbon bonds? I know we just showed how to make carbon-hydrogen bonds. Well, it turns out we make carbon-carbon sigma bonds the exact same way, where we have one of the lobes right here. This is an sp3 hybridized orbital. And this is an sp3 hybridized orbital. And that generates this sigma bond, which is an sp3 sigma bond. Okay, now we don't have that exact same thing happening when we bond carbon to hydrogen, right? Hydrogen only has an s orbital. So that means the sigma bond between the let's say the carbon and the carbon, the sigma bond is going to be sp3 for the carbon, S for the hydrogen. So this is the sigma bond between the carbon and the hydrogen. Okay, so that tells us something other than that. Different types of orbitals combine with different types of orbitals. As long as they're sharing electrons and overlapping in between the nuclei, we have a sigma bond. Okay. And we can have an S bond to an sp3. We can have an sp3 bond to an sp. We can do a bunch of different things like that. So what we want to show you is that there's different ways to do this, but the carbon-carbon first bond we make, that sigma bond, is an sp3 to sp3 bond. All right. Okay, so that being said, what does that look like when it's all done, said and done? Well, we have all these hydrogens that are sigma bonded, and we have this carbon-carbon that is sigma bonded. And if we filled that space with electrons, it would look like this. This is basically the size of the molecule as it's going through space and it's repelling other electrons from the system. So if all tetrahedral molecules are sp3 hybridized and hybridization controls shape, if we change hybridization, we change shape. So let's change hybridization from sp3 to sp2. So that means we have an s and two p orbitals, which means we have a total of 3 orbitals we're blending together. So we should have 3 equal orbitals plus a p that's unhybridized. When we do that, that means we have 3 equal orbitals that have to be spread out in space. Turns out 3 orbitals spread out in space is about 120 degrees. Okay, so what happens? How do we do this? How do we do this? This is confusing, right? Well, again, we started out with our 4 electrons right here. And last time we took all 4 electrons and filled 4 equal orbitals by blending all the p's and the s together. In this case, what we're going to do is we're going to take 2 of the p's and make them hybrid. So we're going to end up with an S is 1 and then the 2 p's. So it's a total of 3. We're going to make 3 equal in energy orbitals and we're going to have 1 electron in each of those. Okay. But we have a leftover p. Okay. So that means the p is going to have to form some other kind of bond. These hybrid orbitals are going to form sigma bonds, direct bonds between other atoms. But that p orbital is going to do something else. But what does that look like? How can we do 3 and 1 and whatever? Okay, well, the way we can do that is if we took the hybridized orbital and the hybridized orbital and the hybridized orbital, that's 3 orbitals. So to spread them out as far as possible, that's 120 degrees. But that makes them flat. All 3 of these bonds are going to be in the same plane. So what that means is the p, if all of our hybrid orbitals are in the xy plane right here, that means the p orbital is in the z axis. Okay, which means it's above and below the plane made by those sp2 hybridized orbitals. So let's try to bond those together. So we're going to bond the first one right here. This is going to be our s to sp2. This one's going to be our S to sp2 because the hydrogen. And this one in the middle is going to be an sp2 to sp2. And they're all sigma bonds. They're all directly in between the nucleus and the nucleus of the neighboring atom. However, we now have these 2 pi orbitals and they're both in the z-axis. Okay, so they're both in the z-axis and we can't do a direct bond because we already have a direct bond right here. So we have to do what we call an overlap bond, where it's above and below the sigma orbital. So because this is in the z-axis, oops, sorry, change color. Because this is in the z-axis right here, it's going to blow above and below part of the time. Remember, that orbital is the electrons anywhere in that space 95% of the time. So 95% of the time, the 2 electrons that are being shared are going to be above and below the sigma bond created by the hybridized orbitals. Okay, so, so why? Why can we do this? Well, it turns out hybridizing to this stage gets us to where we can make newer kinds of bonds. And we know that it hybridized this way because of the shape of the compounds made. So in this case here, if we look at ethylene, which is just 2 carbons and 4 hydrogens, we can measure the bond distance is almost 120 degrees all the way around. Why aren't they exactly 120 degrees? Well, carbons are larger than hydrogens, and so it spaces it out a little bit more than 120 degrees. And hydrogens are smaller than the carbon over here, so they get squeezed together slightly. But overall, they're about 120 degrees apart. And notice that they're all in the same plane. Okay, what that means is that the z-axis is coming above the plane and below the plane. Let me actually do this one this way. Above the plane and below the plane here. Okay, so all of these are our sigma bonds right here. And those 2 leftover p orbitals that aren't hybridized can overlap above and below. So if we did that, we have to look at the structure of the individual atoms, right? The individual carbons are going to look something like this. The carbon atom is in the middle. We have our hybridized orbitals in a plane, and then we have our p orbital, and I'm going to use the z-axis here. This is the y-axis, is above and below that, but it still has an electron in it. So we still have to share that electron to make a bond. And we do that above and below that sigma bond. Right here, this is our sigma bond. That's our sp2 bond. And these are our pi overlap on top, pi overlap on top, pi overlap on bottom, giving us our pi orbital, which is a pz to pc orbital. Okay, because the x and y of the p's are taken up in the hybridization, the last axis has to be unhybridized, and it's the one that makes the other type of bond, the overlap bond, also known as the pi bond. All right, questions on that? So we have sigma bonds that are directly in between nuclei. We have pi bonds, which are overlapped, and you always have a sigma bond before you have a pi bond. So the first bond is always a sigma bond. The second bond is between 2 atoms is the pi bond. So if we look at that a little bit more, and we see that we have this plane created by all the atoms are in this plane right here, and we have this cloud of electrons above and this cloud of electrons below, we can actually see that this cloud is actually kind of really interesting in the fact that, number one, it fills up a lot of space and pushes these even more to be flat. Even if they weren't perfectly flat, those 2 big clouds are going to push it to be flat. But what else does that do? Well, what else that does is that means we cannot rotate the bond between the carbons. In the sp3, you could rotate that bond because we have no other bonds between the 2 carbons, and the hydrogens can just rotate past each other. Okay, but we can't do that once we have a pi bond. The number one reason we can't do that is if we had this in our z-axis and we twisted it out of plane, it would end up going into our x-axis. Okay, it is no longer in the same axis, therefore it can't bond. If you've twisted it out of plane, that means you've broken a bond. You've had to put so much energy into the system to break a bond. Okay, that's why you don't see free rotation around that bond. You only see that it's fixed, and then if you add a whole bunch of energy, you heat it up too much, it can flip, but most of the time it'll stay in that configuration. So because we have, yes, go ahead.
Sorry, I have a quick question. So the point of hybridization, is it to try to make all of the angles relatively the same
It's
or
an,
like similar?
no, it's an explanation on why we see the different structures we have. Okay, we see when carbon has 4 bonds, it'll be tetrahedral. Okay, because of hybridization. When we see carbon with 3 bonds plus a pi bond, it's going to be that flat, 3 of the bonds are going to be flat, and then the pi bond is going to be above and below. Okay, so it's an explanation of why we see the different shapes, or it's an explanation of, you know, the orbitals are hybridized to give us the different shapes, or the different shapes are because the orbitals are hybridized. I look at it as you know, you can look at it from either direction, so that you know if it's tetrahedral, you know it's sp3 hybridized. If it's trigonal planar, you know it's sp2 hybridized. And then we have one more hybridization state to talk about. Does that make sense?
Yes, thank you.
All right. So because we don't want to break this bond just to rotate it, that means we have a restriction around that. And that gives us an interesting problem in the fact that we could have different places in space. Okay, so if we just had this double bond at the end of a chain right here, and we moved this group back and forth just by, you know, just saying we could, it actually turns out to be the identical molecule because it's just flipping this molecule over. We haven't actually broken this bond to change the position of these 2 atoms. Okay, however, if we look at this one right here, we also have not broken a bond to change the position of these 2 groups right here, because all we did was flip it over. Okay, so these are actually the same compound. However, if we have different groups on different sides, we can see that they are going to stay there. Meaning if you make one of these isomers, it's going to stay in that isomer. If you make the other isomer, it's going to stay in that. So what do I mean by that? Okay, so let's look at this. And the first thing we want to do is draw a line through the double bond. And notice that the 2 methyl groups here are on opposite sides of the double bond. One's on the left, one's on the right. We call this the trans isomer, meaning opposite, trans isomer. So it is the opposite sides for those 2 groups. However, if we draw that same line through the double bond, and both of the groups that aren't hydrogen are on the same side, we call that cis, meaning same. Okay, so always in your mind, at least, draw a line through that double bond and see if they're on the same side of that double bond or the opposite sides of that double bond. And that'll tell you whether you have the trans opposite sides or the cis same side. Okay, so why is that important? Well, because we can have the exact same chemical structure, except they'll have different properties because they're actually different, fixed in space. And when we say something's fixed in space, we call them stereoisomers. We have a huge chapter on that in chapter 5. We'll do that more during that time. But I want to show you here that we can do that with groups that are anything other than hydrogen that are substituted. And so the first thing we do is draw our line here. And we see that the chlorine is on the opposite side of the bromine, giving us the trans bromochloroethane. And if we do the same thing for this isomer here, both the chlorine and the bromine are on the same side, so that would be the cis isomer. And I'll tell you now that both of those compounds have different boiling points, melting points, and they have different reactivities because they're different compounds. So we need to pay attention to their specific location in space, specifically because we have that pi bond, which does not allow for free rotation. Okay, questions about isomerization? Okay, we have about 12 minutes less, so we're going to continue on here. So one of the ways to look at this is you're going to want to look at the 2 groups that aren't hydrogen. Okay, so they could be any groups, but the 2 groups that aren't hydrogen on your double bond. So again, always draw that line where the double bond is and look at the 2 groups that aren't hydrogen. In this case, we have this ethyl group and this ethyl group. So it's going to be our trans isomer. We draw our line here. Notice the two hydrogens are also on the same side. And the two groups are on the same but opposite side. That makes it the cis isomer. Now here we have things that aren't the same. Well, let's draw our hydrogen here and our hydrogen here. Our hydrogens are trans to each other, which means this bromo group and this methyl bromo group are trans to each other. So we have the trans isomer. And again, if we draw our line here and put our hydrogens in, the hydrogens are cis to each other. The two other groups are cis to each other. Therefore, we have the cis isomer. Right. Questions about cis and trans isomerization?
What if you have multiple double bonds on the same?
So you would do each individual double bond, I identify it as cis or trans. Now, if you have more than two substituents on a double bond, we actually use a different convention, and we'll talk about that in chapter 3. Okay? This only works for two different things on a double bond. All right. So this is our double bond, and this was sp2 hybridized. So we had 3 equal bonds, the S, the P, and the P, and then we had an unhybridized P that created our pi bond. Well, we can also do that again where we only use one of the P's in hybridization. And when we use one of the P's in hybridization, we have what we call an sp hybridized. Actually, this is wrong. We have an sp hybridized carbon, meaning there's one S and one P plus to go into 2 equal orbitals, plus we have 2 unhybridized p orbitals, okay? Which means that our carbon here can bond 1 sigma bond on one side, 1 sigma bond on the other for these 2 hybridized orbitals, and then it has to have 2 pi bonds for the 2 different p orbitals. Okay, so we have 2 hybridized orbitals, half S, half P, and how do we spread those apart in space? Well, we can spread them 180 degrees apart. So that's why all sp hybridized are 180 degrees apart. And they have 2 available p orbitals to allow them to bond up to twice, giving 2 pi bonds. Okay, so when we see the structure of you have a linear structure between 2 atoms bonded to carbon, it's always sp. When you see 120 degrees between 3 atoms bonded to carbon, it's sp2. When you see four things bonded to carbon and their tetrahedral in structure, it's sp3. Okay, so sp3, 4 equal orbitals, 4 bonds. sp2, 3 equal orbitals, 3 bonds. sp, 2 equal orbitals, 2 bonds. It'll give us sigma bonds always. So hybridization tells us shape, shape tells us hybridization. Okay, so what does this kind of look like? Well, instead of going to the point where we blend all 3 of these, or even 2 of these here, all we're going to do is blend 1 of the p orbitals, leaving 2 unhybridized p orbitals. So we have 2 places to bond. That's 180 degrees apart. And then this is going to be in the X, and then this is going to be in the Z. And hopefully these will all be in the Y right here. So what would that look like? So our hybridized orbitals, oops, wrong. Our hybridized orbitals are the ones right here that are 180 degrees apart. And 80 degrees apart, okay? Which leaves our first p orbital here on the x-axis and our second p orbital on the z-axis, let's say. So that means that the orbital on the z-axis here cannot overlap with the orbital of an x-axis on the neighboring one. Only the 2 p orbitals in that x-axis can overlap each other, which means only the 2 in the z-axis can overlap each other. So what does that look like? Well, that means the one that was in the, oops, not that. So if we look at the, there we go, the hybridized orbital, this is the sp orbital, it's going to pi bond with hydrogen over here. So we have our first, our sigma bond, our first bond, our sigma bond with hydrogen. This one's going to have a sigma bond with hydrogen right here. And then there's going to be a sigma bond between the two carbons. And then this was the x-axis right here. And those are going to overlap to create our first pi bond. And these were our z-axis, the one here and the one out in front here, and the one out in front here. These are our z-axis, and they're going to create the second pi bond. Okay, so whenever we have sp hybridized, we have a linear molecule, then we'll have one pi bond at the x-axis, one pi bond on the z-axis, and the bonding between the hybridized orbitals will be along the y-axis. Okay, so we see how it takes up all the space possible in that structure. Okay, so that means when we do this, our carbon-carbon bond here in the middle is sp-sp, carbon is our sigma bond between the two carbons, and our sigma bond between the hydrogen and the hybridized orbital is an s-sp right there. So what's changing? Okay, well, we're changing the number of p orbitals that can be blended, but we're also changing the shape of things. So what does that mean? Well, in the case of the orbital that is sp, you have half of the orbital is from the s, half of the orbitals from the p. So what we see is that the dumbbell shape is exaggerated on one side. The S is spherical. And so it's going to fill one side of that dumbbell more than the other side. And so we get an exaggerated dumbbell shape. Okay. Now, but in the case of the sp2, we've only got 1/3 s character divided. We have one s orbital divided over 3 orbitals. So that's 1/3. And so we have the same exaggeration, but it's not as big as the sp, but it's bigger than the sp3 because we have one s orbital spread out over 4 orbitals. So it's only 25% s. So the exaggeration of the p orbital is less. So if we look at the lobe on the sp3 is smaller than the lobe on the sp2, which is smaller on the sp. And we're going to learn more about this character, this s character, and how it controls bond length, bond strength, and we're also going to learn about acidity associated. So how do we figure this out? How do we look at this? Well, we want to look at this thing that the more s character, the shorter the bond. Okay, so the more s character, the shorter the bond. So the sp is always going to have a shorter bond than the sp2, which is going to be a shorter bond than the sp3. But in addition to that, we have the pi bond that contributes to that length. So in that case, we see that when we have our sigma bond, which is our sp-sp, and our 2 pi bonds, we have a length of 1.2 angstroms. Okay. Now, in the case of our sp2, so we have sp2 hybridized sigma bond and 1 pi bond, we have a bond length of 1.34. So it's 0.14 angstroms longer. And if we have this and it's sp3 to sp3, we have the longest one at 1.5. So as we go to hybridizing fewer and fewer p orbitals, we get shorter and shorter bond lengths. All right, questions about that? Okay, so we're going to start with VSEPR, or looking at shape versus hybridization, on next Monday. If you haven't already taken the quiz, please go take the quiz by 11 o'clock tonight. If you're having issues, go ahead and email me. Most of the time, just restarting your Canvas and only opening the one thing will usually solve the problem. If you're getting an error that says you need a passcode, that means you need to close your browser and then reopen your browser, maybe even restart your computer to clear out some cache, and then it should automatically take you to the quiz. Okay. All right, I'm going to go ahead and stop sharing and start recording. And if you want to stay behind and ask questions, please do.